Talk to us today about quantitative method for interacting branch distribution. Fontbona, please.
Thank you very much. Today, the next session is also very nice for I can meet here, and I will also like to apologize. The talk is probably a bit more mathematics related. But I will be contributing mathematics. One of you, nothing of the workshop, but I will try to give institutions and motivation that become people who are not students. So this is the joint work with Felipe Munoz, who was my last PhD student. And let me tell you a little bit how the sort of thing will be. So I will start giving a little bit of motivation regarding the models that inspire this work, the type of the population model that inspired this work, which is in the context of it's called Terra contribution models. That way, this is part based in the work we made this years ago, and actually we will focus on a simplified version of this model, because we will be focusing on a specific question, which is something I've been interested in for years. The project is trying to quantify the way in which some microscopic description population converges population of some linear dynamics particle system approach the typically microscopic limit given typically by some linear activity. So that is something very common in the context of input models, and in some extent, what we're doing here is extending some ideas and techniques and results from other contexts where this type of system is more common, and also for longer, which is kinetic theory or the Makimas of concept. Okay? So, as the title said, we will be interested in the convergence rate of some model of interacting branch diffusion processes. And so the main result is the convergence rate of this of the microscopic or individual based to the microscopic dynamics for our simplified model. And I give some ideas of the proof based on Carney constructions or pathways construction of objects in the probabilistic sense, and ideas from which I would say a little bit. Yes, so as regards to motivation, we will take a little bit in general about cross-diffusion models and the specific model we studied or we proposed actually years ago. So this what is called cross-diffusion models are originally there are three models which represent the evolution of new species in environments which interact in several ways. So first of all, there is let's look at this C% here, which is let's say a demographic study. We have some growth of each population. So these are that is used. So let's take the equation for the evolution of U, which is the density of one of the species. So we have this growth term, which is the linear part. Then we have nonlinear terms, which are there's competition between individuals of the population, so U to U, and also individuals of the other species. And here, for each second population, we have and the interesting part here, the most interesting part is what is called the cross-diffusion terms, which are, well, you're probably used to, you have seen this type of dynamics in design. typically, if it was just this term, you have a parabolic linear, and well, this is modeling the diffusion of the population in this case. But you also have this Laplacian acting on this product. So here you have U times U and U times B. So if you develop this, or you can write the weak form if you want to think of it in terms of a stochastic process, what you will see is that, well, at the end, you write the parts and so on, you have a diffusion coefficient given by a constant flat. Diffusion coefficient is Laplacian acting on U, and it's multiplied by U itself and also by B. Okay, so that means that the diffusion at each point for each of the two species is proportional with its intensity is given by the amount of individuals, or the density of individuals at that point of the two times. Okay. So let's say this is a, well, rather classic already model in mathematical and ecology, let's say. And it's a PD model, it's a very hard, actually, PD system. So let me just take a couple of words. I will give you more examples, but rather a very simplified form. But let me just give a couple of words about what is known. So for some time, well, let me try this. Yeah, I didn't write it completely, but yeah, I would say for a long time, what was available local in time work closeness results of regular solutions. And I would say in the last 15 years, the people were able to obtain global solutions, but with type. In particular, you don't have uniqueness, and that mainly because people were able to identify so many spectrum.
Okay.
Yes, yes. I mean, for the atomic spectrum, yes, yes, there are conditions for the so the model we were interested at the beginning with Liebe was not exactly the PD model as it stands here, but a model that we introduced with CDB where what we tried to do was to define an individual-based model, so stochastic microscopic dynamics, so you can represent all the type of interactions. And then, well, the idea is to take some limit the number of some parameter which describes the size of the population, and then obtain some smooth version of these dynamics. The main reason is that if you want to construct the microscopic system, you will have a finite number of individuals, and of course you cannot interact with people with individuals who are at the same point because of the diffusion that you put in individuals who never meet. So you need to find some regularization of let's say evidence. So when you have the density of the population seen as a function, well, it's convoluted in this case with some local care. And then you expect that when you make this kernels go to a direct match, you will obtain the lecture and the reaction. So what we did then was to construct this microscopic description, this individual-based model. I will give some ideas later in a simplified setting of what the model looks like, and then we were also able to prove that when you make these terms, which are simpler in a way because there's no optimization here, so these kernels go to direct methods, you get the standard the reaction terms that respect to the blending. Okay. Sorry? Sorry, yeah, probably is. Yeah, it's not. Yeah, I mean, it does not be the same as PPI. The principle is so yeah, so that left the question open of what happens when you want to make this careless to direct. When you can do it, of course, you need to rely on some structure in the general case. Of course, also we knew more or less that one could do that in local solution. We did not really write that, but it was something that could be expected. But actually, took some time, and I think several people in PDU became interested in this board. And the question that we were leaving open about the convergence with respect to these terms. So I would say, yeah, the first result of that direction, where this was proven to converge for entire but to the actual products that one wants to have, were by Ayman Musa 2 years ago. Yeah, and people as I said, have done other type of results where they forget about this reaction term, and they obtain convergence the equation, but so this is some of the orders of that, but it's really in short time, so it's really not so. But on the other hand, well, you can quantitative, this is really like doing convergence response. So, but you have the 2 points of view and to get everything that you want, but in any case, it's so this is the model, which is the motivation for our work. And what I will talk about in the stories is it will still be in the non-local setting. So we will not be interested in making coefficient methods. But the question we will address is in some sense related to that. The question is the following. The convergence that we obtained with CP, which was proven by weak convergence techniques, yeah, that means can we get in a quantitative? How can we quantify that convergence? And the reason is, as I said, is related or is motivated at least by what happens with the terms here or with the terms here with the regularization, because we would like to we know or we think that the one thinks of the right model is the PDE one, the local one, let's say. And well, we are considering here something which is new. So in our result with PDE, you have converted, you don't have converted, but the regularity here is important. And the question is, we would like to have kind of some diagonal making US of and the interaction scale parameter at the same time. So one step that you need to be able to carry out to get that is to quantify in terms of the regularity here, the coefficients, let's say the each constant of the how what's the velocity, and then you can find the right compromise between the variable and the regularity of the f's. Okay. Okay. So well, it turned out that studying that question in this same setting was already quite difficult. So we made several simplifications. So it would look like I'm very oversimplifying and removing most of the interest of the digital, but still I think we are addressing one specific point that is having been addressed earlier. I don't think in the community or the probability community either, which is well, it could be the main result. So, okay, so we will be dealing with the following model, which is quite simple. Okay? So we will have it will be a binary diffusion that we are diffusion process that we are binary branching, sorry, diffusion process in RD. I will just assume that we have one diffusion. And I will assume that there is interaction of input type in the dynamics of both the drift and the diffusion term, which is like the equation in the beginning. And I will assume that I have a global competition. Okay, so this is true that there is simplification with the original one, because the demographic competition in the model was local or is neighborhood. What I mean by global here is that the competition, or the, let's say, the rate at which individuals die, okay, it depends on the population, but only on the total number, total number. So, well, it's a very particular case. For instance, to take the internet in that part of the it's a simplification, but we have a linearity in the demographic chart. Okay. Asymptotic, yeah, that's correction asymptotic. Yes, yeah, yeah, it's also me. It's also me.
So maybe like you know, technically, that even if you have a longer competition in the living and
Yes.
in the board
Yes, I think it's still pertinent, and it's still needed, as we said. So, and it goes in the right direction. What we did, if we wanted to consider later the local interaction with the technology. But I wanted to the difficulties that will arise. So, but yeah, I think it's simplification, but it's a good simplification. Okay, so you're probably already, sorry, you have already seen this type of expressions here. We have we will represent our process by a measure value process, our population. So presentation is standard. So here I have direct masses at each point of individual. Each direct mass is multiplied by 1 over k. So k is a parameter that associated with current capacity, which is equal to infinity, and more or less measures the size of the population. So each individual is the order of 1 over k. The population size is of the order of constant. It goes in time and more order. And well, this number here is the number of individuals, of course. So it's a price duration, which is this measure. These are the positions of the system. And what is the dynamics? The dynamics is the following. Well, we start with some random point measure at the beginning. And well, there will be death and birth events. So each individual has an independent clock, which is very standard, exponential clocks. And each time I have a birth, well, I add one individual at that point. At the same point, maximum over k. And then, well, this is the competition. Okay, so conditionally that I know the number of individuals, the killing clock, the killing rate of each of them will be this what is this expression. Okay? So I constant times well, the number of individuals divided by k, because I want this rate constant order. And when one individual dies, to remove one direct masses. And what happens between birth and death events? Well, each individual evolves according to a process, which is where you see, again, well, these are the kernels of the nature. Okay, and here you see the type of interaction that we're dealing with. So, at the level of dynamics. So, of course, the drift and diffusion coefficient here can depend on the position of the individual, and it also depends on its convolution with the empirical measure, which you can understand as a smoother version of the empirical test of the test. Okay. So, so in this point, it's also mean field, and as you said, here it's also mean field because you are integrating the empirical measure against one here. Okay, so
the second term, why do you emphasize the dependence on X, the same particle X here?
Here, just to say that, for instance, you can have some influence in the environment.
That's what I understand. Convolution.
Here.
Yeah.
Yeah, because it's a convolution of the empirical measure with the kernel, but I look at it in the position where I am. Okay. So here it's local, I mean. Regularized local. Yeah, here with H and G, and here you can take the photo later. But that's okay. Okay, so yeah, a remark is that which is important in this for work is that if you just look at the number of individuals, just to be a logistic branching process. In particular, it's autonomous. It does not depend on where the individuals are. It's just a counting process. Greater. So it's a various process with some dynamics which is this. Well, this is the simplification of a particular case actually of the reproducibility, which is that under some regularity assumption, convergence of the initial condition, the measure, positive measure. One has convergence of the process quickly to the unique solution of calculated, which is a linear evolution TDE. So where you get here, this can start with the action of this differential operator, and you see that this differential operator is nonlinear, depends on the T as well. Okay, so which is kind of what you get in the Joaquín context, and this is what you end up with the part of the logistic interaction. Okay, so this is double. So still you have a linearity here, and of course you have linearities. Okay, so a couple of simple remarks that this process, so the type, the number of individuals by take converges to the map, to the map of this unity. And if you just integrate here against one, this part disappears, and you realize that the map satisfies the another remark which is interesting and also important for our purposes is that if you normalize here this solution divided by its mass, it turns out that this satisfies also a nonlinear equation which is, I would say, close, or nearly close, in the sense that you have here an evolution of mu bar. Here you don't have mu bar, you have mu, but you have a relation between mu and mu bar because it's the normalized version, and the map is something which is in the room. So this is really kind of like particular of the working paper. Okay. This will be important, and I will mention it later. Why? You will see why, but let me mention that if you take the non-local interaction here, it becomes you get something quite strange here. You don't get a diffusion. Remember here you have a diffusion operator. So you would expect that if you divide here, you get something which is close to a diffusion operator, and that's what happens. But if this is non-local, you make this division. What you get is that diffusion jump equation, which is when you meet an additional term of order one, you try to do something like that, and you realize it's a jump. Okay, but anyway, we will not be working on that in that sense. Okay, so what is the main result? Well, we have some assumptions which are natural. We will assume that the initial conditions are I, B, and I would take a fixed positive measure U0 as an condition, which I can normalize and use as law for my position. So that would be an assumption. Could be simplified, but I will assume that. Well, there are some more instructions. I will be denoting by representation the dual bounded ellipse on the space of finite design measures, which for those of you who know what this problem is, this metrises the good convergence of finite positive measure. And the result is the following. Well, we will be looking at the difference of the distance with respect to this distance, to this norm, one norm of the mu t, which is the solution of the integral process. So a finite interval for each k, given k fixed, we have as an explicit bound, which of course goes to 0 when the case goes to infinity. This is a simpler there, which I here. And this is some explicit function that goes to 0 polynomial rate, which I will show in a while what it is. But the interesting point here is what is this rate? I mean, where it comes. Okay. So
how the digits means that the constant function.
It's bound and digits. Digits unknown.
But the constant is not.
Ellipses, no. I mean, it means it will mean that you're in a hole. You're bounded.
Yeah.
Okay, so what is this convergence factor? So in order to make it before making it explicit, well, this is where well, it's better to so you probably know this what I'm going to say now. So well, let us recall what the battle in this place. So we start with this morning. So this is a distance between probability measures and finite infinite over measures of the product space with marginals out of the given measure of probability measure that we have. But we have the relative properties. We probably know for sure, which is and the nice thing about this distance is a counting distance. It means that you have this type of inequality for each standard you can construct two random variables with those you want in the center of the space, but each for this. And something which is very important for construction is that for the result is that counting always exists. Well, we need more than that, but I will. And the main ingredient, the source of the convergence rate is the result by Nicola years ago, which gives an explicit rate of convergence for empirical distributions of I. Okay, so it's quantitative low French number for empirical distribution, which states that if you have I examples in low with some moment. Yeah, there are several parameters, but we chose one of those. So in that case, well, we're dealing with the P equal to the expected square Wasserstein distance between the distribution of these random variables and their empirical measure of a sample size n is bounded by some constant type times this function which appears in our okay. Here it's squared because this is the order of the square. So if you take the square root of this modest, it's the same function as we had, except that we were evaluating it at k, is the current capacity, which is not a number of things, it's just k, and here it's n, which is is the number of particles. Okay. So yeah, so
Is it addition in the number?
yes, I mean if they are independent, you can do that. That works at times.
Yeah.
So that's the idea. So the idea is yeah. So this is something many people, in particular, I students have used a lot, and I think a lot of machine learning topics. It's not very very. B is the dimension of the space.
So this is like a point of a summation. Like what? So this is starting with the law of large numbers and the point.
Summation.
No?
Yeah.
For our friend from ecology, and we toss points, we have that.
Yes, I mean this is in particular the information about all the empirical means. I mean you take average or more. Yeah, it's a considered. But so it contains much more information that is the means functions that but all the means. Okay. Okay, so and what is the function now? So I will show it, but it's not really necessary to understand what it is. So it goes to zero polynomially, and well, according to the parameters, you have not the same. Right?
Q the moment.
Q is the moment. You assume that you have finite Q.
Depending on the diffusion, that's a different frame.
Depending on
The dimension.
yes, yes.
Very.
Yeah.
And dimension, why dimension 4?
There, yeah.
Why dimension 4
Yeah.
is important?
Yeah, I don't know. I mean, I remember when it's I couldn't give you an okay. So to state it short, what we're doing is comparing a rate versions of independent objects to its limit towards this object which are empirical measure, which is of course if you know about a little bit of correlation curve, policy, no, but in that case you deal with fixed n, and you make n go to infinity. And of course, to go in variation of chaos, I would say the ideal type of result that you want to get is to show that you're infinite interacting objects, they converge to some deterministic object or some nonlinear object in the limit at the rate which is the same of law of large in the language that you're using. So in this case, it would be, I mean, let's say, in the models, you would aim to this, to get this. Okay. So actually, yeah, the thing is, how can we transfer this to a setting where we don't have n particles, but of the order of k particles that are trying to evolve in an interaction. So let me give an idea of the proof and of the tools that we are using. Yeah. So let me just make a couple of simple remarks, which you can easily check, is that this dual bound reaches distance between both the measures, not necessarily for the measures, you can call for them by the Biostochastic one distance between the normalized version, so times the map of one of them, and the map. Okay. And also from the other direction. But this is the one we were using, and well, we'll be using Biostochastic 2 because it's different for the different processes and so on, because we have interaction in the so yeah, as Simon remarked, it is not hard to transfer the bound to to a context where, well, not, we are assuming that we are allowing ourselves to have a random number of individuals, but if conditionally on the number of individuals, like their positions are IV, I can just use their bound with conditional expectation instead of expectation. Okay, so here I use the bound we have here. And what you will there is which you try here to after applying this term here is bounded, and what you do simply is that, okay, this is of the order of n, this n random n to some negative power smaller than 1, and to something here at the denominator, so we can cancel with this one. And I mean, it will not cancel, what you will have is here an n to some power which is smaller than 1. So this allows you to get rid of some k here and put it outside of the order of the exponent, and which is you get again something which is here the same exponent as here, and like which equals or just something like that, you can put it again outside. Okay, so what you end up is having something bounded times the k to some power here, which is exactly the k that appears. Okay. So I mean, at time 0, under assumptions in which we have conditional in the number of individuals, we have independent IID particles. It's very easy to transfer it. So the question, of course, is what was the problem? Which is log as soon as t is 0. What is the idea here is what can we do? The problem is so. What will be the main in this proof? As in many of these proofs and problems, it's very useful to have a capital construction, which means that you construct. I mean, you want to show that something converges to something to another thing, or you want to control to estimate the difference between them, and that distance, if you remember, is expressed in terms of you can control it in the case of particle system. Let's say, in terms of the expectation of the physical distance, let's say, between two random variables that have those. So that's the motivation for constructing couples. You will construct in the same probability space, in this case, well, our original calculus conventional process, and a different process, which I would like it to have the same features or nice properties that we had at time 0, which is that conditionally in the number of individuals, they are independent, and they have the right law, some law which is good for what I got, which in this case, imagine is the normalized version of the solution of the equation. Okay, so, well, so in this specific case, we will also have to right. So this is very useful for important part of the work. Is that they have the same mass, and that means that the birth and death events are the. I mean, one way of getting that is that they. For which it is certainly important that the mass is autonomous. The total number of individuals is reduced. Yeah. And then what I will ask is that these particles are what I just said, that conditionally on the map. So they are ID particles and they have the law of the normalized nonlinear numbers. Okay. You can law. So okay, so the idea is to construct that. I mean, you have many ways of doing that. Don't get solved, but let me say what is the first kind of thing that we can observe in the construction is that Well, I would like I mean, if you remember well, I need to bound something like this because this was the control for the boundary things was part of the other one was the map in the map discussion. So, so what I can do is to compare my particles, my new particles independent with their log, and then I need to compare the distances of the normalized version to the two particles. Okay, so that's natural. Okay, so as I said, for the first condition, well, the coupling implies that we will use the same quantum point processes to write the chunks, the demographic events. That's simple. For the second one, which is that I want these particles to be independent, given their number and their law to solve this equation, I will use, I mean, yeah, at each time, well, if I know how many there are, I will ask this particle to follow this evolution, which is the multimodal or the nonlinear process, process type that we would associate to this thing. Okay. So the only difference with standard multimodal is that here in standard multimodal we have V bar. Now we have two, which is the non-normalized. And there is something which is important here that condition. I want this to be the law conditionally on the number of individuals. And actually, one can check that, well, the number of individuals is random. But what I will do, I mean, and each one is given birth at some random time. But if I make them, if they are given birth at a random time, let's say tau with the right law at that time. So this is a random time, but the law is the one that corresponds to the position at the time. If the particle has been aligned from the zero, from time zero, well, this satisfies the condition. Okay, so there are three things which are not completely fixed. You probably know this is. Let me solve found out what we get with this part of the construction. Of course, once we have this term, I can control it this way as the time zero, particular conditional independent given n and the row is this one. So one needs to control, of course, in cabinet construction, the distance between the two constructors. So, well, here is implicit the fact that if we forget about this k, when you put n t k here, what you have is the Biostochastic distance between a coupling of the two particle system, which is I match the names. Okay, if you just put here nk. Okay, so what I'm doing is no. It's that this is smaller than this divided by nk. So okay. So that's here's where the, let's say, coupling nature of this distance is. Okay, so I need to control the evolution of this of the distances of the couplings that I make. I didn't mention it, but well, I will mention it now here. Yeah. So of course you can always do whatever you want with your coupling as well as the marginal laws, the dynamics that you want of the processes. Half is the right one. Okay. So in particular, something I didn't say, but probably yesterday is that some natural choice to do to keep these particles close is to make them be driven by the same problem. It's a natural choice. There are better choices actually, okay? But for the sake of simplicity, I mean, for what we need, it's enough to do that. And actually, yeah, the Lipschitz coefficients, the fact that the coefficients are Lipschitz, and that you can do several several times. It turns out that it is enough to keep this distance control during the evolution. Okay, I mean, if you a particle is giving birth in one of the system, some particle is giving birth in the other one, and you during the evolution, but they will not go too far from each other because you have this control and they're following the sequence. That's quite nice. But the thing is that that will control what happens when the particles are giving birth. And well, here you know what happens when the particle is giving birth. It's because some individual that particle that is born took place where some individual relation is. The thing is, what do you where does this individual, the corresponding individual, independent position depends? Where does that appear? So you have the choice. Okay. So we make the following observation, and it is that, well, of course, you would like them to be born in well, this we know it's somewhere. It's the inverse of the position of one of the particles. This one we haven't decided, but you can remark that, well, choosing one individual here in the original population, if birth is equivalent to choosing one individual with the empirical measure of the population at that time, or let's say just before the. And on the other hand, well, we don't know. I mean, we don't know where this will be born, but we know the law. Start the law, okay, so the idea would be to couple this to birth position in an optimal way. So the optimal way is to sample the birth position of the individuals using the optimal coupling of two things: this empirical measure and this deterministic, this given probability. Okay. Okay, so that's the idea, and you need some technical because yeah, this is being sampled from a quantum point process, and you want this to be sampled measurably with respect to the predictable sigma p and stuff. So yeah, there is a measurability result which generalizes something we have to obtain it in B like 15 years ago for random particular system. So well, the thing is that you can do that. I mean, at each point that you have, at each time that you have a birth, you can sample simultaneously one of the particles that give birth, which is has this empirical law, and one particle somewhere which has this. Okay. So we do it in the optimal way, that means the sampling from the optimal coupling to a distance. And let me yeah, we're drawing. So this is, well, you can already imagine what's the idea. So here I have the original system. At some time I have a verb, which in this case must be here. Then this is binary branching. And what happens here is that this is new tau here. So I have at the same time a verb, and the idea is that this point, or this point which is random, is coupled in an optimal way in average to this to this. Okay. Then you leave this body, and then again you have a verb here, and again, okay, now you have an empirical measure here, choose from supported 2 points. So I chose this particular to branch, so I choose a position sample according to again the law of bar, which is close enough.
The ultimate is always to the right.
No, yeah, and so on. So of course, something which is nice of the coupling contraction is that if you do the right thing, okay, this is, I mean, this process or this system doesn't know about the other one, right? Okay, so I think from here, this is born somewhere, okay, somewhere which has this law, a position which has this law, and so on. This is born somewhere, and a position but it turns out to be close to the position where it is. Okay. And that we
Standard.
no.
Because the connection you can convert to the other, or the coupling has to be the
Yeah. Okay, yeah. And then of course the bird, the time steps. Okay, so well at the end what you end up doing is to yeah, so this is you start with this close to this, and then you know that this you know that this the law so this is close to the physical measure independent condition within the particles, and this is comparable to this comparing, so you get a longer and the remainder terms are but because everything is expressed in terms of the ultimate some probably measurement physical ideas. Okay. Okay, so that's it. Question.
Here you have one species.
Yes.
When you went for two.
Yes.
Does that have some political stuff?
Yes. Yes. Well, it was not the number of species.
Because you should include
Yes, but you have to make more physical processes. But then the independent of different sizes. Yeah, it's not the main problem. You want to generalize. I think the main problem is that what I said in one is that if you would like to go one step further, is that you would like to use local space interaction neighborhood, and then you don't have the same number of individuals.
Yeah,
so you need to decide who you're going to couple with whom. Some of them you will need to couple, and on the other hand, which looks like an additional difficulty, is that the process, the original processes that you're considering are diffusion processes, but the natural processes to couple with are independent copies of something, which I said it's not a linear diffusion in the sense of the thing, the diffusion jump by some reason. I mean, so it looks like you have two additional diffusions, but I think they cancel. They should cancel in the sense that the jump term in the one process, they should put you doing the capping. But we have an idea of that, but we have to make the challenge. Yeah, for a PhD student, no, but that's it's not necessarily. Yeah, it could be, but I think the main there's something we don't understand completely. I think that you don't have the same number of particles. It looks like they will, of course, if the dependence on the position is regular, when they go to infinity, it will be close in any case. So it will be constant. But the thing is that this jump term is you must interpret it in order to do the right coupling, to choose the good particles to couple with. Because the interpretation that's not very confident. The for future work, and for the very confident. Okay, and yeah. Here, any other
question? I think maybe I made a question like throughout the talking you're building this something you're showing that is we have maximum covariance of the end human achiever of minimum distance for the few top right?
Not very especially because well, the pro is not is when you go to the measure to the whole measure. I'm not sure that you are could do better, but it's also because once they are born, well, it evolves in time with random motions and more or less parallel, let's say, but it gets worse than optimal. The thing is that when they are giving birth, they are covered in the ocean.
It's good enough.
Yes.
You're sort of the EL norm, you want to found that. Measure moment, then see the video students go, why not stay at back in 2 minutes away? I think it's the same thing about part of your work.
I mean, yes. Because because of several reasons, first because the path of time and I have the conditionality of the mass. Also because well the objects that are given are finite measures, so not probability measures. So yeah, it's really because of that. So I would say the for those of you who know classical argument, what I mentioned is about variation of chaos, that you couple with independent things. So here you will guess construct conditionally given design. And actually you have a type of variation of chaos. Okay, so it's still you can state it, but it's not very clear how to say it. But so I would say the central point that we end up addressing here, which was not the intention at the beginning, but was to transfer the variation of quantitative chaos techniques available for, let's say, genetic modes to population modes where you don't have a constant population.
There is no question, please.